In the context of the Gross-Neveu-Yukawa (GNY) chiral Ising transition, researchers have long expected that various methods, including conformal bootstrap, perturbative renormalization group, and quantum Monte Carlo (QMC) simulations, would yield converged critical exponents. However, this expectation has not been fully realized due to obstacles introduced by the UV finite size effect. This work addresses this issue by employing the elective-momentum ultrasize (Emus) QMC method to compute the critical exponents of the O, N, 2, squared Z GNY N equals 8 chiral Ising transition on a 2D pi flux fermion lattice model. The model describes the transition between Dirac semimetal and quantum spin-Hall insulator phases, and the Emus QMC method allows for the matching of fermionic and bosonic momentum transfer and collective update in momentum space. The results provide fully consistent exponents with those obtained from the bootstrap and perturbative approaches. Specifically, the critical exponents Eps, F, and Nu are found to be 0.72, 6, 0.04, 2, and 1.07, 12, respectively, which are in agreement with the latest estimates from E-expansion and conformal bootstrap. The Emus QMC method is designed to overcome the limitations of previous lattice model simulations, where the critical bosonic and fermionic modes were not properly matched, leading to significant drifts of the exponents in finite size analyses. By simulating two patches near Dirac points in momentum space and using a collective update scheme, the Emus QMC method effectively accesses larger system sizes and better data quality with reduced computational cost. The relevance of this work extends to the study of interacting Dirac fermion systems, including Dwave superconductors, nematic quantum criticality, graphene, twisted bilayer graphene, and other quantum moire materials. The consistent results obtained in this work demonstrate the power of the Emus QMC method in exploring the vast ocean of conformal field theories, CFTs, and providing a solid foundation for understanding quantum phase transitions in interacting Dirac fermion systems. The research paper discusses the study of the chiral Gross-Neveu-Yukawa (GNY) Ising critical point using the entanglement momentum space quantum Monte Carlo (Emus QMC) method. The authors investigate the critical behavior of the model, which consists of fermions and bosons interacting via Yukawa coupling. The Emus QMC method is employed to simulate the linear region of the Brillouin zone (BZ) near the Dirac points, which is crucial for understanding the critical behavior. The authors first introduce the model, which includes the fermionic Lagrangian, L fermion, the bosonic Lagrangian, L boson, and the coupling term, L coupling. The model is designed to study the chiral GNY Ising transition, where the bosonic field acquires a non-zero expectation value, leading to a gap opening in the fermion dispersion. The Emus QMC method is then applied to simulate the model, focusing on the linear region of the BZ near the Dirac points. The results of the simulation are presented in Figure 2, which shows the square of the bosonic order parameter, S, gamma, and the correlation ratio, R, as functions of the control parameter, M, for different system sizes, L. The data collapse of S, gamma, and R is performed to extract the critical exponents, 1, Nu, F. The authors obtain 1, Nu equals 1.07, 12, and F equals 0.72, 6, which are consistent with previous studies. Furthermore, the authors calculate the fermion anomalous dimension, Eps, by monitoring the imaginary time-Green's function, as shown in Figure 3. The result yields Eps equals 0.04, 2, which is consistent with the expected value. The authors also verify the consistency of F equals 0.72 obtained from the data collapse. The Emus QMC method is shown to effectively reduce the finite size effect, allowing for the simulation of larger system sizes with less computational time. The authors conclude that the Emus QMC method is a powerful tool for studying critical behavior in interacting fermion systems. The authors present a comprehensive study of the N equals 8 chiral Ising Gross-Neveu-Yukawa (GNY) model using the elective-momentum ultrasize (Emus) quantum Monte Carlo (QMC) method. They report the critical exponents Eps and F, which exhibit robustness with increasing system size, consistent with the conformal bootstrap and E-expansion results. The EMUSQMC method is shown to be efficient, consuming fewer computational resources than previous simulations. The results are compared with previous studies using QMC, E-expansion, and conformal bootstrap, demonstrating textbook-level consistency of the critical exponents. The authors highlight the potential of EMUSQMC to investigate various GNY transitions, including those in graphene and twisted bilayer graphene systems. The authors also discuss the concept and implementation of the EMUSQMC method in the supplementary material, including stochastic data collapse to extract critical exponents unbiasedly. They provide details on the implementation and validation of the EMUSQMC algorithm. The study contributes to the understanding of GNY transitions in 2D quantum systems, particularly in the context of quantum materials. The results have implications for the study of nematic order, intervally coherent and valley polarized orders, and superconductivity in these systems. The authors acknowledge the support of various research grants and computational resources, including the Research Grants Council of Hong Kong SAR of China and the High Performance Computing System at the University of Hong Kong. Key equations and concepts include critical exponents Eps and F, which characterize the GNY transition, elective-momentum ultra-size, Emus, quantum Monte Carlo, QMC, method, which combines momentum space QMC with the ultrasize scaling analysis. Stochastic data collapse, a technique used to extract critical exponents unbiasedly from simulation data. Notable findings include consistency of critical exponents with conformal bootstrap and E-expansion results, robustness of critical exponents with increasing system size, efficiency of EMUSQMC method compared to previous simulations. Limitations and future work. The study is limited to the N=8 chiral Ising GNY model, and further work is needed to generalize the results to other models and systems. The EMUSQMC method requires further validation and testing in different contexts. Future work will focus on applying the EMUSQMC method to other GNY transitions and quantum materials. The supplementary material for Emus live on the chiral Gross-Neveu-Yukawa archipelago discusses the EMUSQMC scheme, a variation of the conventional DQMC simulation. In this approach, the focus is on small patches of the Brillouin zone, BZ, that are significant in the infrared limit, ignoring the effects of momenta far from these hotspots. The model used is a 2D chiral Gross-Neveu-Yukawa model, which has 2 Dirac points as its hotspots. By working in momentum space, the simulation can be performed fully on momentum space and flip the bosonic fields directly on their momentum components. This reduces the computational complexity and improves efficiency. The fermion part of the model is block diagonalized into 2x2 matrices describing hopping between 2 sublattices at each of the n=LXLK points. The coupling term is a summation over 2 momenta, and after flipping any phi q, the changed entries in HC are those whose momenta differ by q. Thus, delta is not needed to save as a full NF² matrix, it is block diagonalized by groups of momenta that are related by q. To improve the efficiency of the simulation, several adjustments were made. Firstly, the amplitude of change in the bosonic field CQ was optimized to avoid proposing changes with too small acceptance rates while keeping the update significant. Secondly, CQ is larger when the updating momentum Q is closer to gamma, as phi q should have larger magnitude on average. Lastly, calculating the bosonic interaction, phi I phi j, squared in real space is time-consuming, so it was expressed with their Fourier components, and only phi q pair interactions with appropriate coefficients were considered. This significantly reduced the time complexity in this part. The rest of the simulation follows the usual DQMC scheme. The fermion weight of each specific bosonic configuration is given by y_sigma equals det, I plus b_sigma, beta, 0, where b_sigma is defined as b_sigma, L_2 increment tau, L_1 increment tau, equals L underscore 2 Y underscore L equals L underscore 1 plus 1 E caret. Increment tau H underscore C, phi, L, E caret, increment tau H underscore F. When an update is proposed on the LTH imaginary time layer, one has det, I plus B, beta, L increment tau, E caret, increment tau H underscore C, phi, L, E caret, increment tau H underscore F, equals det, I plus B, beta, L increment tau, I plus delta, B, L1, increment tau, 0, where delta is defined as delta equals E caret, increment tau H underscore C, phi, L, E caret, increment tau H underscore C, phi, L, I approximately equals E caret, increment tau, H underscore C, phi, L, H underscore C, phi, L, I. Here is the combined summary. The acceptance rate in the Monte Carlo simulation is calculated as the ratio of weights, which is further simplified using the Sherman-Morrison formula to obtain an expression involving the determinant of a matrix. This matrix is a function of the equal time Green's function, G, which is defined as the expectation value of the product of fermionic operators. The final expression for the acceptance rate, RF, is the square of the absolute value of the determinant of this matrix. In the context of stochastic data collapse, the authors employ a method similar to that in references 59, 60 to collapse the order parameter data shown in Figure 2, C, and D. This involves fitting a line to the collapsed data and evaluating the goodness of fit using the R-squared value, which is a widely used statistical measure. The R-squared value is defined as 1 minus the ratio of the sum of squared residuals to the total sum of squares. The authors use weights that decay exponentially away from the critical point to focus the fitting process on the critical regime. The data collapse procedure involves scaling the data obtained from different system sizes according to a set of critical exponents, fitting a single curve to all the points, and calculating the ratio f, which measures the variation between the rescaled data and the fitted value. A small value of f indicates that the set of exponents produces collapsed data that can be well explained by a single curve, thereby validating the exponents. This method is used to test various sets of critical exponents and determine which ones provide the best data collapse.